channel. So in today's session, let us have a look on a block cipher algorithm. So in the previous session, we have seen the difference between a stream cipher and a block cipher, and also we have seen the design principles of a block cipher, and in the very recent class we have seen the Feistel structure. So whatever the algorithm which follows the processing in number of rounds and plain text, dividing the plain text into two equal halves and performing the round functions and applying the individual keys in each and every round, and later swapping of two halves. So if any block cipher algorithm which follows all these terms, then we can say that algorithm is following the Feistel structure. So most of the block cipher algorithms will follow the Feistel structure. So among those, in today's session, let us have a look on one type of such block cipher algorithm which follows the Feistel structure is DES algorithm. A very important algorithm, that is a DES algorithm. DES. So it stands for Data Encryption Algorithm. So this algorithm is a block cipher algorithm. That means the plain text is processed to the cipher text in number of blocks. So here the block size of a plain text is 64-bit. So at a time the 64-bit plain text is processed to get the cipher text. Next, so it follows the Feistel structure. So it blindly follows the Feistel structure. So here the plain text is processed in number of rounds. So number of rounds to implement this DES algorithm is 16 rounds. So totally it requires 16 rounds. Next, key size. Here the key size is also 64-bit. So in some materials you will find it is as a 56-bit. But actually the key size is 64. So from this 64 it will be converted into 56. So later I will explain it. Next, as we have seen in the Feistel structure, if any block cipher follows the Feistel structure, that means the plain text is processed in number of rounds. Each round should have a separate independent key. That means here the key size is 64. So we are having 16 rounds in this DES algorithm. So totally we have to generate 16 subkeys. So number of subkeys, 16 rounds there we are processing, so we require 16 subkeys. Now the question is, what is the subkey size? Subkey size. So here the subkey size is 48-bit subkey. So this is the plain text, 48-bit subkey. So from the 64-bit key we have to generate 16 48-bit subkeys. So in each and every round we are supposed to use the subkey, each subkey. So these are from 1 to 16 subkeys. So finally cipher text, the result of this DES algorithm, that means the cipher text, size of a cipher text is, so here we are considering 64-bit plain text. So obviously we will get the 64-bit cipher text. So this is a simple overview of DES algorithm. The first and foremost point is it follows the Feistel structure. So if it follows the Feistel structure, It's a block cipher algorithm, so block size is 64-bit. So if number of rounds, so plain text is processed to cipher text in number of rounds. So in the DES we have to implement 16 rounds, and the key size is 64-bit key, and from this 64-bit key we have to generate 16 48-bit subkeys, so where each subkey should be used in each round, and finally we will get the cipher text as 64-bit cipher text. So this is a simple overview of a DES algorithm. Now let us move on to the block diagram of DES algorithm. See, coming to this block cipher algorithm, the first point is, here we will use some transposition orders which are predefined. So we have to arrange the bits in the given order. So that is fixed. So we have to follow the order, transposition order. So here the transposition order means rearranging the bit positions, which we have seen in the transposition ciphers. So like that, in like the transposition techniques, here also we will use a more number of transposition orders. So here in number of times we are required to rearrange the order of bits. So there is some order given, so I will show you that order. So we have to follow the order in order to implement this DES algorithm. So first let us see the block diagram of DES, and then we will move on to the next step. So first and foremost, we have to consider the plain text, and we have to apply the initial permutation. So this is the initial permutation. Here we have to give 64-bit plain text. So here the transposition order, we call it as a permutation. So wherever the permutation concept came, there we have to follow the transposition order, which I will show you in the next coming minutes. So here the 64-bit plain text is given as input to the initial permutation, where we have to follow the transposition order. So that means we have to rearrange the bit positions, and from this we will get again 64-bit as output. So this 64-bit will be given to a round 1. So in this round we have to use a key. So parallelly we have to generate the subkeys which we have to use in the round function. So parallelly I will write here So here the key is also, as I have said, it is 64-bit key. For this 64-bit key, first we have to use permuted choice 1. Permuted choice 1. So the input for this permuted choice 1 is 56-bit key, and the output for from this is 56. So the input is 64-bit, the output is 56-bit key. And from here we have to apply left circular shift operation. Left circular shift operation. From this we will get again 56-bit key. From that we have to again apply permuted choice 2. So here also the permuted choice means rearranging the bit positions. So from this we will get the key which is of 48-bit. Hope you understood. first we have to consider the 64-bit key, and this should be given as input to the permuted choice 1, where the transposition order will be given. So according to that transposition order, we have to rearrange the bits. So in that purpose, some 8 bits will be ignored, and the output from this permuted choice 1 is 56-bit, and this is given to the left circular shift operation. So depends upon the round, how many bits we have to shift is given in the example, given in the algorithm. So depends upon the round function, we have to consider how many number of bits should be left circular shifted. So the output from this LCS is 56-bit, and that is again given to the permuted choice 2. Here the permuted choice 2. So here also we have to follow the transposition order, where again 8 bits will be ignored, so that we will get the 48-bit key, which is used in the round function 1. So this is key 1. Again, after round 1, again apply round 2. Again apply round 2. Again, after this circular shift, once again give to left circular shift. Again you have to perform the left circular shift operation. So how many bits we have to shift is depending on the round number. So again this is a 56-bit key. Again this is applied to the permuted choice 2. Where some bits will be ignored. So this is 56-bit key, and from this we will get 48-bit key 2. Similarly, we will follow the same procedure till round 16. So we will follow the same procedure till the round 16. So here also we will use left circular shift operation. So the number of bits to be shifted depends upon the round number. So from this we have to give into the input to the permuted choice 2. From this again we will get here 56-bit is given to PC2. Here 48-bit will be output from PC2. So key 16. After completion of all these rounds, we have to perform 32-bit swap. So we have to perform 32-bit swap. Here it is a 64-bit. We have to divide it into 2 equal parts, 32 left half and 32 right half. Those 32-bit will be swapped. That means exchange. The left 32 will be copied to the right side. Right 32-bit will be copied to the left side. So after completion of this 32-bit swap, again we have to apply inverse initial permutation. Inverse initial permutation. So here this inverse initial permutation is also the transposition order. So where we have to rearrange the bit positions. So the output from this is a cipher text. So this is the block diagram of DES algorithm. So first consider the 64-bit plain text, give it as input to the initial permutation. So where we have to rearrange the bit positions of this plain text, and the output of initial permutation is again given as input to the round 1, where the sub key is generated, key 1 is generated, and key 1 is used in the round 1. And then the output from round 1 is given as input to the round 2. Similarly, here the second key is generated with a 48-bit, and this key 2 is again used in round 2. And the output of round 2 is given as input to round 3. So likewise we have to complete until round 16. So after completion of round 16, the output of round 16 will be given as input to the 32-bit swapping. That means now we have to exchange the 2 equal 32 halves. So after exchanging, it will be given as input to the inverse initial permutations. Once again we have to rearrange the order. So here we are rearranging the order, so that's why we have to again rearrange the order of the positions, I mean order of bits. And the output from this inverse initial permutation is the final cipher text, which is a 64-bit cipher text. So this is the block diagram of DES algorithm. Now we have to elaborate this round function. This round function, that means what actually happens in this round function. So parallelly we are generating the subkeys. So here 16 rounds, so 16 subkeys should be generated. And in each round, what is happening? That means what operations or what functions will be applied on round function. So let us see the round function now. So let us see the round function now. So first, the 64-bit is divided into 2 halves. Left half, right half. And similarly, let us consider the key. Key is also divided into 2 halves. Left key and right key. Okay, now so this is a 32-bit and this is also a 32-bit. This is 28-bit and this is also 28-bit. So we have to divide it into 2 equal parts. So this one, the 32-bit is given as input to the expansion permutation. Expansion permutation. So here this is the 32-bit. After giving the 32 as input to the expansion permutation, as its name indicates, we have to add 16 more bits and this completely becomes a 48-bit. So that means additional 16 bits will be added in this expansion permutation. So that's why the name indicates expansion. So we have to add more number of bits. And this must be XORed. This must be XORed with key. Now, first we have to use left circular shift. So apply the left circular shift. Here also left circular shift. And after this left circular shift, we have to apply for the permuted choice 2. So this will be given to permuted choice 2. So here also it will be 28 and 28. And from this we will get 48. 48-bit key 1. So here some 8 bits will be reduced. So this can also be called as contraction. That means reducing the number of bits. Here we call it as expansion, here contraction. That means reducing. So after XORing this, we have to apply this 48 bit to S boxes. S box. S box is called a substitution box. So the input for this S box is 48 bit and the output from this S box is 32 bit. Again, some bits will be reduced. So 48 will be reduced to 32 bit. So after coming from the S box, again apply the permutation function. Apply the permutation function. That means again this is a transposition order given by the DES implementation. So here also we have to rearrange the order of bit positions. So from this we will get 32 bits, and this will be XORed with left half. This will be XORed with left half, and this will be stored in R, and this will be stored in left half. Right? So these are the inputs for the next round. So L and R are the two 32 bits, and this 32 bit will be expanded to 48 bit, and parallelly the key will be generated, the sub key is generated of 48 bit, so which is XORed with the expansion output of expansion permutation, and that 48 bits will be given as input to the substitution boxes, where it will be converted into 32 bits. Some 16 bits will be reduced, so 32 bit will be generated, and this 32 bit must be given as input to the permutation function, where again we have to follow the transposition order to rearrange the bit positions, and the output of permutation function will be XORed with the left 32 bit and stored in the right half, and the right half is stored in the left half. So these two will be input for next round, and here also after applying this left circular shift, store it in LK, store it in RK. So here these two are the inputs for the next round. That means next key generation. Inputs for next key generation. These are the initial inputs, and these are the inputs for the next key generation. So this is the actual round function. Round function of DES. Round function of DES. So here we have to see what actually happens in the expansion permutation, S boxes, and the permutation, and the permutate choice too. Now let us see one by one so that you can clearly understand, right? So first let us start from the beginning, block diagram. So considering the 64-bit plain text. So after considering the 64-bit plain text, we have to give that 64-bit plain text as an input to the initial permutation. So here the initial permutation, see, this is the block diagram. So coming to this block diagram, here we have given the 64-bit plain text to the initial permutation. So where we have to rearrange the order of bit positions. That means we have to follow the transposition order. So before applying the initial permutation, for easy understanding, we will represent this 64-bit as 8 by 8 representations. That means 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on, 16, 17 and so on, 24, so on, 64. So for easy representation, we are representing this plain text as 8 by 8 table. So applying to initial permutation, first applying to initial permutation, so we have to follow the procedure. That means we have to follow this initial permutation, the transposition order, where the 58th bit will be in the first position, 50th bit will be in the second position, 42nd bit will be in the third position, and similarly 7th bit will be in the last position. So blindly we have to follow this transposition order. So in the DES algorithm, so this will be the transposition order of initial permutation. So after this initial permutation, I mean after arranging this order of bit positions, again consider this as a first position, second position, third position, fourth position. So actually the plain text, in the plain text, the first position will be the 58th bit, second position will be the 50th bit. So now we are rearranging the order of bit positions according to the given transposition order. So after initial permutation, so again we have to give the output of initial permutation to round 1. So in that round 1, the first thing is we have to divide the plain text into two halves. So this is the right half, this is the left half, and this is the right half. So the right half is given as input to the expansion permutation. So expansion permutation means we have to expand the number of bits. So here the input for this expansion permutation is 32 bit and the output from this expansion permutation is 48 bit. So 16 bits will be added in this expansion permutation. So this is the transposition order given to which we have to follow for the expansion permutation. So arrange 1, 2, 3, 4, 5, 6, so and so 32, and these 16 bits will be added. So 32nd bit will be added once again, 4th bit 8, 12, 16, 20, 24, 28, 5, 9, 13, 17, 21, 25, 29 and 1. So these 16 bits will be added so that the complete length of this expansion permutation becomes 48. So the input is 32 and the output is 48. We are adding 16 bits. So after applying to this expansion permutation, so we have to XOR the output of expansion permutation with the permuted choice 2. That means the output of permuted choice 2. So for this permuted choice 2, we have to generate the subkey. For this, so as I have said that in the block diagram, the key size is a 64 bit, and from this 64 bit we have to apply that 64 bit as input to the permuted choice 1. So where we have to again follow the transposition order. So here again we have to follow the transposition order given for this permuted choice 1. So simple thing is, here just in the permuted choice 1 we will eliminate the multiple of 8 bits. That means 8, 16, 24, 32. So all these bits will be eliminated. So you can observe you can't find the multiple of 8 bits in this permuted choice 1. So this is the output of permuted choice 1. So the input for this permuted choice 1 is 64 and the output is only 56 bit. So that 56 bit is again given to the left circular shift. So we have to apply the left circular shift. and that 56 bit is again divided into two equal halves. So here we can see two equal halves, so left half and right half, so 28 bit and 28 bit, so total 56 bit. So after applying the permuted choice 1, the output of permuted choice 1 is 56, so that 56 is again divided into two halves, 28 and 28, and that 28 bit is given as input to the left circular shift. So the number of bits to be shifted depends upon the round number. See, so depends upon the round number, how many bits we are going to shift. So in the round 1, round number 1, round number 2, round number 9 and round number 16, we have to perform 1 bit circular shift operation. So 1, 2, 9 and 16. So in all these 4 rounds we have to shift only 1 bit, and in the rest of the round numbers we have to shift 2 bits. So we have to apply the 2 bits left circular shift. So after applying the left circular shift, we will get again we have to give this output of left circular shift to permuted choice 2. Once again we have to apply the transposition order, where the 56 bit key will be reduced to 48 bit. So that's why here we can see it as permutation or a contraction. Permutation or a contraction. Contraction here means reduces the number of bits. So here the permutation choice 2 is applied. So here the permuted choice 2 is also the transposition order which we have to follow in the DES algorithm. So this is the permuted choice 2, where we have to rearrange the bit positions according to this transposition order. So here some 8 bits will be reduced. So 56 bit key will be reduced to 48 bit after applying this permuted choice 2. So some 8 bits will be reduced. So according to this bit positions we have to rearrange the bits. So output from this permuted choice 2 is a 48 bit. So input is 56 and output is 48. And now the output from this permuted choice 2 is given XORed with the output from the expansion permutation. See, here the output from this permuted choice 2 is XORed with the output of expansion permutation, where we got a 32 bit to 48 bit. So output of this XOR operation is again 48 bit. So obviously, so this 48 bit will be applied to the substitution boxes, where again the 48 bit will be reduced to 32 bit. So let us see this operation, how this substitution box, how that 48 bit will be reduced to 32 bit. So here we will apply this S boxes, transposition boxes, substitution boxes. See, so in our DES algorithm there will be total 8 S boxes. So the input for S box is 48. The output from the S box is 32 bit. So this 48 bit will be divided to 8 S boxes. That means, so each S box, S1, S2, S3, S4, S5, S6, S7, S8. So each S box will get 8 bits as input. 6 bits as input. Right? So 8 S boxes, so 6 bits as input. So 6 bits. 6. So the output from this each S box will be 4 bit. So 2 bits will be reduced. So total will be 8 fours 32 bit. So that means the input is 48. The input is 48. The 48 is divided to 8 S boxes, and each S box will take 6 bit as input and it produces 4 bit as output. So let us see. Each S box will be having input 6 bit and output 4 bit. So how this 6 bit is reduced to 4 bit? Let's have a look. So if you consider, if you consider 6 bits, let it be 1 0 0 1 1 0. If you consider these 6 bits, these are the 6 bits. The first bit and the last bit represents the row number. So here the S box is a table of numbers. S box is a table of values. It's a table of values. So obviously if it is a table, we must know rows and columns, right? So here the first and last bit, first plus last bit represents row number, and the between 4 bits represents column number. So the first and last bits, that means 2 bits, right? So here 2 bits, here 4 bits. So what is the maximum number we can represent using 2 bits? So the combinations are 0 0 0 1 1 0 1 1. So the maximum number is 3. And how many combinations? 4 combinations, right? So 4 choices. So there will be 4 rows in our S box, and here it is 4 bits. So the maximum number we can represent using the 4 bits is 1 1 1 1, and the least number is 0 0 0 0. So this is a 15, 0, this is 0. That means total 16 columns will be there. So our S box consists of 4 rows and 16 columns. So here the 4 is represented as 0, 1, 2, 3, numbering of rows. 0th row, first row, second row and third row. And the column representation is 0, 1, 2 and so on 15. 0th row, first row, second row and so on 15th row. 15 column. So in this example, let us see the first and last bit, that means 1, 0 represents the row. So 1, 0 means, what is the decimal number? It's a 2. Second row, and the remaining bits, in between bits, 0 0 1 1. So here 8 4 2 1. So it is a column number. It represents the column number 3. So we have to consider this table of values, and we have to consider the corresponding element with a row 2 and a column 3. So let us have an example. So each S box will be having 4 rows and 16 columns. So this is a sample S box which is having 4 rows and 16 columns. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. Total 16 columns and 4 rows. 0th row, first row, second row, third row. So in our example, we got a second row and a third column. See, second row. Here, second row is 0th row, first row, second row. And the third column, 0th one, 0th column, first column, second column, third column. So here the value in the third column is 0, 1, 2, 3. So here the third column is 8. So the result of this one is 8, which is again represented in a binary format. So 8 is represented as 1000. So the output of this 6 bits is 1000. So this is for S1. So like this table, we will be having total 8 tables. That means 8 S boxes. Each S box is having 6-bit input. So from that 6-bit input, we have to consider the first and last bits as a row number and the remaining 4 bits as a column number. And in the table, we have to find out the corresponding value of given or calculated row number or a column number. So here in this example, we are taking 100110 as input, 6 bits. So first and last bits 1 and 0 represents the row number, and the last in between 4 bits represent the column number 3, 2 and 3. So we have to consider the value in the second row, third column. So second row is 0th row, first row, second row. Third column is 0th column, first column, second column, and the third column. The value is 8. So 8 is again represented in binary value. So 1000. So which is the output of S box 1. So likewise, we have to consider, we have to calculate the output from all the 8 S boxes. So here each S box is containing 6-bit input, and we will get a 4-bit output. Totally we will get the 32-bit output from the S boxes. So here in the DES, the security will lies on the S boxes, right? So similarly, we will have total 8 tables. 8 tables. So after getting the output from the S box, and we are applying the permutation for the obtaining output. That means 32-bit will be, again we are applying to the permutation. That means again we have to follow some transposition order. So the permutation for this transposition order is for this one. So here the length of the bits will not be changed, only the 32-bit. The arrangement of bit will be changed. So we have to rearrange the bit positions according to the given transposition order. So we have to follow this order. So no bits, so the number of bits will not be reduced or number of bits will not be added. So the input for this permutation is 32, and the output from this permutation function is also 32. Here only the rearrangement will be done according to the given transposition order. So here the 16th bit will be in the first position, 7th bit will be in the second position, 20th bit will be in the third position, likewise. So after applying to the permutation, the output of permutation function is 32-bit, and which is XORed with the left 32-bit. So in the starting position, in the initial stage, we have divided the plain text into 2 halves. This left half is now XORed with the output from the permutation, and it is stored in the right. And rightmost 32-bit, before applying to this expansion permutation, it will be given, it will be stored in the left half. Left half. So these two will be the inputs for the second round, and before applying to the permuted choice 2, the output from the left circular shift will be given as input to the next round. Here we will see C and D. So here these two are the inputs for next round, for the next key generation. Here these two are the inputs for the next round of the plain text processing. So this is a single round which is applied in the DES algorithm. This is a complete single round function. So we have to follow the same round function 16 times. So after completion of 16 rounds, we have to apply the 32-bit swap. So that means the left half will be stored in right half and the right half will be stored in the left half. So 32-bit swap will be done. again here we will get the 64 bit. So after that, after applying this 32 bit swap, this 64 bit will be again given to the inverse initial permutation. So initial permutation we have applied, so we have to apply the inverse initial permutation, where we have to rearrange the order of bit positions. So here also the input is 64 and output is 64, so no bits will be added, no bits will be discarded. So whatever the input we are giving to the inverse initial permutation, we will get the same number of bits as the output. So this is the final permutation function. Inverse initial permutation, final permutation, that called inverse initial permutation. Again we have to rearrange the order of bits in the given transposition order. So this is the ciphertext. So the output of this final permutation or inverse initial permutation will be the ciphertext. See, the inverse initial permutation, the output from the inverse initial permutation is the 64-bit ciphertext. So likewise we have to apply this DES algorithm in 16 rounds, and in each round we have to apply the round function. Parallelly we have to generate the subkeys from the given master key, and each subkey will be XORed, used in each round. And here we have to use a left circular shift, perform the left circular shift according to the round number. The number of bits should be left shifted. So in the round numbers 1, 2, 9 and 16, 1 bit left circular shift should be applied, and in the rest of the round numbers we have to perform 2 bits left circular shift. So this is the complete round function. So the important thing is S-box conversion. Here 8 S-boxes will be there. So each S-box will be having 6-bit input and 4-bit output. So in the 6-bit, first bit and last bit will be considered as a row number, the decimal value of 2 bits, and the decimal value of the in-between bits will be represented as a column number. So the 2 bits, the maximum number representation with the 2 bits is 3. That means the combinations are, the possibilities are decimal values 0, 1, 2 and 3, total 4 rows. And a column in between 4 bits, we will get the maximum number 15 and the minimum number 0. So each S box will be having 4 rows and 16 columns. The numbering for rows is 0, 1, 2, 3, and the numbering for columns is 0, 1, 2, 3 and so on 15. So we have to consider the decimal values, and we have to consider the corresponding decimal value and convert that corresponding decimal value to binary value. So this is the S box. So we have to consider the corresponding row value in the corresponding row and column, and we have to again convert it into the binary value. That means we have to represent it into a 4-bit representation, so that we will get the output as 4-bit. So after combining all these 4 bits from the 8 S boxes, we will get 32-bit. So this 32-bit will be again given to the permutation function, where the permutation, that means rearrangement of bits, will be done, which is XORed with the left half, and the rightmost 32-bit will be saved in the left, which is given as input to the next round, and the output from the XOR will be saved in the right, which is given as input to the next round. So hope you understood this DES algorithm. If you are having any doubts regarding this DES algorithm or any concept in the network security, feel free to post your doubts in the comment section. Definitely I will try to clarify your doubts. And if you like my videos, share my videos with your friends and subscribe to our channel. Thanks for watching. Thank you very much.